So now let's look at the air conditioning process or different processes that are associated with air conditioning. Maintaining a living space or an industrial facility at the desired temperature and humidity requires some processes called as air conditioning processes. These processes include simple heating, that is basically raising the temperature, simple cooling or lowering the temperature, humidifying, that basically means adding moisture, and dehumidifying, which is of course removing moisture. Sometimes two or more processes are needed to be combined to bring the air to the desired temperature and humidity level. Various air conditioning processes are illustrated in the psychrometric chart here given in figure 14-19. Notice that simple heating and cooling processes appear as horizontal lines on this chart since the moisture content of the air remains constant, or omega would be constant during these processes. Air is commonly heated and humidified in winter and cooled and dehumidified in the summer. Notice how these processes appear on this psychrometric chart. Most air conditioning processes can be modeled as steady flow processes with the following general mass and energy balances. The mass balance could be written as mass flow rate that is coming in is going to be equal to the mass flow rate out. When you are thinking of just dry air, the summation of all the flows that are coming in is going to be equal to the summation of all the mass flow rates going out of the system in kilograms per second. And in terms of just water, the flow rates of water, all the flow rates that are coming in would be equal to all the mass flow rates of water that are going out of the system, or could also be expressed in terms of the mass flow rates of dry air coming in times the humidity ratio. The summation of all of these flow rates coming in would be equal to all the flow rates going out, which is going to be the summation of mass flow rate of air times the humidity ratio of all the flows that are going out from the system. In terms of energy balance, the total energy flow rate coming in would be equal to the total energy flow rate going out, and this could be expanded to the heat flows coming in plus the work coming in terms of rate plus all the mass flow rate times enthalpy. All of the flows coming in would be equal to the heat flow rate going out and the work flow going out plus the mass flow rate times enthalpy of all the flows going out. The work term usually consists of fan work, which is small relative to the other terms in the energy balance relation. Now let's look at simple heating and cooling processes where the specific humidity or omega would stay constant. Many residential heating systems consist of a stove, a heat pump, or an electric resistance heater. The air in these systems is heated by circulating it through a duct that contains the tubing for the hot gases or the electric resistance wires, as shown in this figure 14.20. The amount of moisture in the air remains constant during this process since no moisture is added or removed from the air. That is, the specific humidity of the air remains constant, or omega remains constant during a heating or even a cooling process with no humidification or dehumidification. Such a heating process proceeds in the direction of increasing dry bulb temperature following a line of constant specific humidity on the psychrometric chart, which appears as a horizontal line as we discussed earlier. Notice that the relative humidity of air decreases during a heating process even if the specific humidity omega remains constant. This is because relative humidity is the ratio of moisture content of the moisture capacity of air at the same temperature, and the moisture capacity increases with temperature. Therefore, the RH of heated air may be well below comfortable levels, causing dry skin, respiratory difficulties, and an increase in static electricity. So a cooling process at constant specific humidity is very similar to what we talked above, except the dry bulb temperature decreases and the relative humidity increases during such a process, as you can see in figure 14-21. Cooling can be accomplished by passing the air over some coils through which a refrigerant or chilled water flows. The conservation of mass equations for a heating or a cooling process that involves no humidification or dehumidification reduces to m dot sub A1 would be equal to m dot A2, which also would be equal to the m dot sub A for dry air, and omega 1 would be equal to omega 2 of water. Neglecting any fan work that may be present, the conservation of energy equation in this case, you can see that it reduces, or the capital Q dot would equate to m dot sub A times the enthalpy at state 2 minus enthalpy at state 1, or the simple Q would be equal to enthalpy at state 2 minus enthalpy at state 1. Here you will notice that H1 and H2 are enthalpies per unit mass of dry air at the inlet and the exit. Now let's look at heating with humidification. Problems associated with the low RH resulting from simple heating can be eliminated by humidifying the heated air. This is accomplished by passing air first through a heating section, that is process 1 to 2 in the figure 14-23, and then through a humidifying section, which is process 2 to 3 in figure 14-23. The location of state 3 depends on how the humidification is accomplished. If steam is introduced in the humidification section, this results in humidification with additional heating where T3 is going to be higher than T2. If humidification is accomplished by spraying water into the air stream instead, part of the latent heat of vaporization comes from the air, which results in the cooling of heated air stream where T3 is going to be less than the value of T2. Air should be heated to a higher temperature in the heating section in this case to make up for the cooling effect during the humidification process. Let's now look at cooling with dehumidification. The specific humidity of air remains constant during a simple cooling process, but the RH or relative humidity increases. If the relative humidity reaches undesirably high levels, it may be necessary to remove some moisture from air, that is, we have to dehumidify it. This requires cooling the air below its dew point temperature. The cooling process with dehumidification is illustrated schematically and on the psychrometric chart in figure 14.25 as you see here. Hot moist air enters the cooling section at state 1. As it passes through cooling coils, its temperature decreases and its RH increases at constant specific humidity. If the cooling section is sufficiently long, air reaches its dew point state X, saturated air. Further cooling of air results in the condensation of part of the moisture in air. Air remains saturated during the entire condensation process, which follows a line of 100% relative humidity until the final state, which is state 2, is reached. The water vapor that condenses out of the air during this process is removed from the cooling section through a separate channel. The condensate is usually assumed to leave the cooling section at a temperature of T2. And as you can see in this particular example, the T1, the higher temperature is 30 degrees centigrade, and after dehumidification, the temperature T2 is going to be 14 degrees C. Now let's look at the evaporative cooling process. Conventional cooling systems operate on a refrigeration cycle and they can be used in any part of the world, but they have a high initial and operating cost. In desert environment where there are hot and dry climates, we can avoid the high cost of cooling by using evaporative coolers, which are also known as swamp coolers. Evaporative cooling is based on a simple principle. As water evaporates, the latent heat of vaporization is absorbed from the water body and the surrounding air. As a result, both the water and the air are cooled during the process. This approach has been used for thousands of years to cool water. A porous jug or pitcher filled with water is left in an open shaded area. A small amount of water leaks out through the porous holes and the pitcher sweats in a dry environment. This water evaporates and cools the remaining water in the pitcher, as you can see in figure 14.25. You have probably noticed that on a hot, dry day, the air feels a lot cooler when the yard is watered. This is because water absorbs heat from the air as it evaporates. An evaporative cooler works on the same principle. The evaporative cooling process is shown schematically on the psychrometric chart in figure 14-27. Hot dry air at state 1 enters the evaporative cooler where it is sprayed with liquid water. Part of the water evaporates during this process by absorbing heat from the airstream. As a result, the temperature of the air stream decreases and its humidity increases, which is given in state 2. In the limiting case, the air leaves the evaporative cooler saturated at state 2-. This is the lowest temperature that can be achieved by this evaporative cooling process. The evaporative cooling process is identical to the adiabatic saturation process since the heat transfer between the airstream and the surrounding is usually negligible. Therefore, the evaporative cooling process follows a line of constant wet bulb temperature on the psychrometric chart. Note that this will not exactly be the case if the liquid water is supplied at a temperature different from the exit temperature of the airstream. Since the constant wet bulb temperature lines almost coincide with the constant enthalpy lines, the enthalpy of the airstream can also be assumed to remain constant. That is, the wet bulb temperature is going to be approximately constant during the process, whereas the enthalpy is also going to be constant. This is a reasonably accurate approximation that can be used in air conditioning calculations. Now let's look at adiabatic mixing of air streams. Many air conditioning applications require the mixing of two air streams. The mixing is accomplished by simply merging the two air streams as shown here from pipe 1 and pipe 2 combining into pipe 3. The heat transfer with the surroundings is usually small and thus the mixing process can be assumed to be adiabatic. Mixing processes normally involve no work interactions and the changes in kinetic and potential energies are negligible. Then the mass and energy balances for the adiabatic mixing of two air streams can be depicted as you see in this slide. In terms of mass of dry air, the mass flow rate of dry air in pipe section 1 plus the mass flow rate from section 2 would equate to the total mass flow rate that is going out from section 3. And when you are talking about mass of water vapor, the humidity ratio of section 1 times mass flow rate of air coming in from section 1 plus omega 2 times mass flow rate from section 2 would be equal to omega 3 times mass flow rate of section 3. And in terms of energy, the mass flow rate of air from section 1 times the enthalpy of that air in section 1 plus mass flow rate of air in section 2 times enthalpy of that air would equate to mass flow rate of air on section 3 times its enthalpy. and eliminating mass flow rate of section 3 from above relations, we obtain that mass flow rate of air from section 1 divided by mass flow rate of section 2 would be equal to H2 minus H3 divided by H3 minus H1, where H would be the enthalpy. Now let's talk about wet cooling towers. Power plants essentially are large air conditioning systems, and some industries generate large quantities of waste heat that is often rejected to cooling water from nearby lakes or rivers. In some cases, however, the cooling water supply is limited or thermal pollution is a serious concern. In such situations, the waste heat must be rejected to the atmosphere, with cooling water recirculating and serving as a transport medium for heat transfer between source and the sink, which is the atmosphere. One way of achieving this is through the use of wet cooling towers. A wet cooling tower is essentially a semi-enclosed evaporative cooler. An induced draft counter for wet cooling tower is shown schematically here. Air is drawn into the tower from the bottom and leaves through the top. Warm water from the condenser is pumped to the top of the tower and is sprayed into the airstream. The purpose of spraying is to expose a large surface area of water to the air. As the water droplets fall under the influence of gravity, a small fraction of water, usually a small percent, evaporates and cools the remaining water. The temperature and the moisture content of the air increase during the process. The cooled water collects at the bottom of the tower and is pumped back to the condenser to absorb additional waste heat. It should also be noted that makeup water must be added to the cycle to replace the water lost by evaporation and air draft. To minimize water carried away by the air, drift eliminators are installed in the wet cooling towers above the spray section. The air circulation in the cooling tower described in the previous slide was provided by a fan, and therefore it is classified as a forced draft cooling tower. Another popular type of cooling tower is the natural draft cooling tower, which looks like a large chimney and works like an ordinary chimney. The air in the tower has a high water vapor content, and thus it is lighter than the outside air. Consequently, the light of air in the tower rises and the heavier outside air fills the vacant space, creating an airflow from the bottom of the tower to the top. The flow rate of air is controlled by the conditions of atmospheric air. Natural draft cooling towers do not require any external power to induce the air, but they cost a lot more to build than forced draft cooling towers. The natural draft cooling towers are hyperbolic in profile as shown in this figure. The idea of a cooling tower started with the spray pond, where the warm water is sprayed into the air and is cooled by the air as it falls onto the pond, as you can see in this figure. Some spray ponds are still in use today. However, they require 25 to 50 times the area of a cooling tower. Water loss due to air draft is high, and they are unprotected against dust and dirt. We could also dump the waste heat into a still cooling pond, which is basically a large artificial lake open to the atmosphere. Heat transfer from the pond surface to the atmosphere is very low or very slow. However, we would need about 20 times the area of a spray pond in this case to achieve the same cooling. For calculations associated with cooling of a power plant by a cooling tower, you'll have to use the equations that are presented here. So first you'll have to do a dry air mass balance, and then a water mass balance, and then do an energy balance for the system considering all the inlets and the outlets.